Okay, we're going to start our wave unit by learning a little bit about some of the different types of waves and learn some of the vocabulary. But first off, we need to talk about what are waves all about. Waves are all about energy transfer. You throw a rock into the water, and it's going to make ripples that are going to travel out from that one spot. You only made a disturbance in one place, but it's going to travel elsewhere. The most important thing to remember about waves is that the disturbance only moves the particles locally, but the energy can travel outward from there. All right, so breaking waves into their different types. So one of the ways that we can categorize waves is whether they can transmit their energy through a vacuum. And just like back when we did free fall, vacuum doesn't mean that thing you use to clean your floors. Vacuum means empty space. Okay? So the first type we're going to talk about are called electromagnetic waves. These are waves that don't need anything. They can transmit their energy through a vacuum. Light is a good example of electromagnetic waves. I'm sure you can think of some other ones. Radio waves, your cell phone uses electromagnetic waves, all of those kinds of things. The other main family we're going to talk about are called mechanical waves, and it's what we'll use mostly in this unit. Mechanical waves are not capable of transmitting their energy through a vacuum. They require something called a medium, more on that in a minute, in order to transport the energy from one location to another one. A sound wave is a good example of a mechanical wave, kind of the most common one that we'll use. There are some others. All right, so what was that word medium? The medium is the stuff that the wave is going to travel through. It's the stuff that moves, that the disturbance is going to move to transfer the energy from one place to the other. If this is water waves, then the medium is going to be the water molecules. A little more common one for you guys. Think about a stadium wave. We start doing the wave in the stadium. The medium is the fans, and you can imagine if you took away the fans, of course, you would have no wave. Same thing with other mechanical waves. If you didn't have anything in your medium, there wouldn't be a wave. Okay, normally this time of year, we'd be playing with slinkies right about now. In this case, your medium is going to be the slinky itself. We would be showing you how you make a disturbance in one end, and then energy is going to travel all the way to the other end. Particle might move up and down or backwards and forwards. Either way, it's going to return. Those little particles of slinky are going to return to where they were, what we call their equilibrium position, but the energy is going to transport from one end to the other. So a couple of different versions of that for you. We will also make a distinction between a pulse and a wave. They're similar. A pulse is just going to be one single disturbance that's going to travel through the medium from one place to the other. If it repeats over and over again, what we call periodic, that's going to be what we actually refer to as a wave. But both of them are going to behave kind of the same way. Okay, so our first way of breaking up waves was either electromagnetic or mechanical waves, and it had to do with what they can travel through. The other way we can categorize them is by the direction of the disturbance. So first off, can you tell that we like slinkies around here? Look at these and think about how would you describe the difference between the two types, the transverse wave and the longitudinal wave. I'll give you the actual definitions here in a minute. Okay. In a transverse wave, the particles, the slinky in this case, is going to move perpendicular to the direction of the wave travel. In this case, my wave is traveling from left to right, but the hand is moving the particles, the little bits of slinky, up and down. Those are transverse to each other. So the key words you want to remember are transverse, perpendicular. The other category of waves are called longitudinal waves. In those, your particles are going to move parallel to the direction of the wave travel. Again, in this case, my wave is traveling from left to right, but in this case, we're pushing on the slinky in a left and right motion as well. So those two are going to be parallel, longitudinal, parallel. Those are your keywords you want to remember. Okay, a couple of other examples of transverse waves, and then I'll give you some other examples of longitudinal waves. Okay, so first off would be your stadium wave is a transverse wave. The people jump up and down, but the wave goes from side to side. If you look at that crazy looking wave full of dots, pick one of the dots. Just pick one and look what it does. It's moving up and down. It's just moving in little small motions, but it's transferring the wave energy along. That little particle doesn't actually go anywhere. The little black dot on the left-hand side never ends up on the right-hand side. Okay? Here's a good example of a longitudinal wave. In this case, notice that your particles, and in this case it's got a little arrow on one of the red ones, you can see that it's just moving left and right and causing little bunches in the wave. Okay. For these kind of waves, we call those bunches compressions, and the spaces in between them are called rarefactions. Sound waves are a really good example of longitudinal waves. If you were to look at the particles of air, the air molecules as you speak, this is basically what's happening. You're getting these little compressions where they bunch up together and then they spread out, and then your wave is going to transfer from one place to another. Okay, what about water waves? Those are pretty common. Well, a water wave is an example of something called a surface wave. And what you will see is, if you notice the little diagram, you're getting much bigger motions up on the surface than you do down below. And if you get deep enough, you get almost no wave motion at all. Okay? These are actually they're undergoing what we call circular motion. So if you look at one particle, they're making little circles. If you've ever been fishing and used a floater or a bobber, you can watch them do kind of the same thing on the surface of the water. They're not really longitudinal and they're not really transverse. They're kind of a combination of both. Okay, so what can the different kinds of waves tell us? So why is this important? Well, this is just one example, but earthquakes, when the earth shakes, it makes both transverse and longitudinal waves, and those are going to travel through the earth. A couple of things we call the seismologists, the people who study these things, call these P waves for the longitudinal waves and S waves for the transverse waves. And they travel at different speeds and they look different when they look at the seismograph. And so they can see when these things are arriving. There's also a couple of other kind of different waves created in earthquakes, but these are the two main ones. Okay, so here's where this gets important. When seismologists started studying earthquake waves, they noticed that only the P waves, the longitudinal ones, made it straight through the core of the Earth. We end up with this thing called a shadow zone on one side of the Earth, where you only see the P waves and you don't see any of the S waves. So this is how they were able to determine that the Earth core has a liquid core to it. We measure them around. So when you think back to elementary school, when you learned that the Earth's core was liquid, this is how they actually know that, which I thought was kind of cool.